In this video, we are going to be talking about gases collected over water as a result of a chemical reaction. This is an application of Dalton's law of partial pressures. So when we go into a lab and we do a chemical reaction that produces a gas, if we want to quantify how much gas is produced, we can collect that gas over water, which means we run a tube and we pump that gas into water. The gas that's collected here in the collection chamber displaces water, pushes the water out the bottom until the reaction is complete, and then we can make sure that the heights of the liquid inside and the liquids outside are equal so that the pressure inside is equal to the atmospheric pressure outside. Then we know that our atmospheric pressure, our total pressure, is equal to the sum of the gases inside. But since this is liquid water here, all liquids have a small amount of gas molecules of that substance that exist above the liquid. That means that this collection of gas molecules inside here consists not only of the gas molecules we're interested in, but it also contains some of these gaseous water molecules. So according to Dalton's law of partial pressures, the total atmospheric pressure, which is this outside of in the atmosphere pressure, is equal to the pressure of the gas that we're actually interested in and the partial pressure of the water vapor that's also in there. The pressure due to the water vapor in there is completely dependent on the temperature of the water. It's not dependent on how much water there is, it's only dependent on the temperature of that water. The vapor pressure of water increases fairly exponentially as a function of temperature. The vapor pressure has been tabulated, and so here's a table of vapor pressure versus temperature. So whenever you're trying to do this in a lab, there are tables where you can look up the vapor pressure of water as a function of temperature. There are more precise tables than this one that tell you down to the decimal point what vapor pressure that is, but we'll be using this table for now. So here's an example problem of how this calculation would go. It reads, the decomposition of potassium chlorate produces oxygen gas and KCl. If 124 milliliters of O2, that's my volume of O2, is collected over water, so this is my P total, at 20 degrees Celsius, how many moles of O2 are produced? So I know that my P total is equal to my pressure of oxygen gas plus my pressure of water vapor, which will be equal to, I'll just start a new line. So 762 millimeters of mercury is equal to my pressure of oxygen gas plus my vapor pressure of water. I can use this temperature to look up on the table what my vapor pressure of water is. My vapor pressure of water is 17.5 millimeters of mercury. I just got to make sure that this unit matches that unit. So now I can do some subtraction, and so my pressure due to oxygen gas will be 762 minus my vapor pressure of water. And so that's going to be 744.85 millimeters of mercury. I'm just going to underline that 4 there so that I remember that that was the last significant digit. Nope, I did not type that in right. That is 762 minus 17.5. I had an extra 1 in there. That's 744.5 millimeters of mercury. That makes a little bit more sense. Okay. I was wondering how subtracted 1/2 and I ended up with an 8. I had to double check my calculator entry. Okay, so now it's asking for my pressure of my how many moles of O2 are produced. So I'm looking for moles. So my moles of O2 can be due to my pressure of O2 times my volume divided by RT. That's my ideal gas law equation rearranged. And we know that that's my partial pressure of O2, and that's my moles of O2. So that is 744.5 millimeters of mercury. And then my volume is 124 milliliters. And so that's 0.124 liters. And then for my R, I'm going to use the torr value, which is 62.36. And then that's liter. And then since the torr is a millimeter of mercury, I'm just going to write millimeters of mercury per mole Kelvin. And then my temperature, again, is going to be plus 273 of that. And so that is 293.15. So now I can type this into my calculator, 744.5 times 0.124 divided by 62.36 times 293.15. And so my moles of oxygen is a really tiny number, 0.0050499. How many 6 do I need? That had 3. That's going to have 3 by the time I expand that. And so that is 5.05 times 10 to the minus 123. 5.05 times 10 to the minus 3 moles. Here is a practice problem for you. Vinegar and baking soda react to form carbon dioxide gas according to this balanced equation here. If all of the carbon dioxide gas is collected over water at 18 degrees Celsius, the total volume of gas is this on a day where the atmospheric pressure is that, and the vapor pressure due to water is this at 18 degrees Celsius. What mass of baking soda was used, assuming there was excess of vinegar? Go ahead and pause the video and try to work this out. Unpause the video when you're ready to check your work. Okay, so let's go over this. So if I know that my total pressure is equal to the sum of my carbon dioxide gas plus my pressure due to water vapor, because this whole thing is collected over water. So that is going to be 768.00 millimeters of mercury is equal to my partial pressure due to carbon dioxide, and then it's telling me my vapor pressure of water, 18.76 millimeters of mercury. I can solve for my partial pressure of CO2, and that will be 768 minus 18.76, and that is 749.24 millimeters of mercury. It's not letting me write that close to the boundary here with the split screen. So that's millimeters of mercury. So now I can calculate my moles of carbon dioxide gas using the ideal gas law, knowing that that's going to be dependent on my partial pressure of CO2 times my volume divided by my R and my temperature. And so that is 749.24 millimeters of mercury times my volume. Gotta divide that by 1,000, 0.03233 liters. And then my R I'm going to use the same R that I did in the past example because millimeters of mercury and torr are the same. And this will make my unit conversion life easier. And then what is 18 plus 273.15? That is 291. Okay. So I can now type this in and I get 749.24 times 0.03233 divided by 62.36 times 291.15. And so my moles of carbon dioxide gas 0.00133 for moles of CO2. But that's not what the question's asking for. The question's asking for grams of this compound. And so I have to back calculate. I now have moles of this. So now I have to figure out moles of that so I can get into grams. So I have to cancel out my moles of CO2, get into moles of sodium hydrogen carbonate. That's messy. Use your imagination. One of each. And now I have to go from moles to grams of that sodium hydrogen carbonate. And let's see, did I save that in my calculator from before? Let me find out. Okay, I couldn't find it in my calculator, but I did recalculate it. I stored my mole number as C, and so if I take my moles and I multiply that by 84.006, that's a 1. I should end up with my answer. And so that is 0.1121 grams of the sodium hydrogen carbonate.